Hi everyone, my name is David Sanchez-Cid. I'm a postdoc at the University of Zurich, and I would like to start by thanking the organizer for this opportunity. On behalf of the Dark Energy Survey collaboration, I will be presenting the analysis framework behind the DS-ER6 weak lensing and galaxy clustering results, how we built it, how we validate it, and what it taught us for the next generation of surveys. So the Dark Energy Survey mapped the southern sky from 2013 to 2019 using a 570 megapixel camera at the Cerro Tololo in Chile. The wide field covers 5,000 square degrees in 5 photometric bands down to limited magnitude in the I band of 24. This enables both geometry probes like the baryonic acoustic oscillation and supernovae, and also growth of structure probes through weak lensing and galaxy clustering. So the GR6 catalog is the full legacy dataset with 140 million galaxies. This is a 40% higher number than in the GR3, the previous iteration, with redshift reaching up to 1.16. So this is same footprint as the previous iteration, but significantly more statistical power. So this increase in precision is exactly when theoretical systematics start to matter. If your model is slightly wrong at small scales, you can no longer hide behind the noise. This is the core motivation behind this work, building an analysis framework that matches the quality of the data and extracts cosmology in a robust and unbiased way. And the tool that we use to do that is the 3x2-point analysis. So the core of our analysis combines the 3 2-point correlation functions of the cosmic shear, the galaxy-galaxy lensing, and the galaxy clustering into what is called the 3x2-point analysis. Each probe constrains cosmology differently. Cosmic shear and the 2 times 2-point combination have orthogonal degeneracies in the omega m S8 plane, and together they deliver tight constraints. The bridge between these measurements and the cosmology is a theoretical model. And building that model is what I will show you in this presentation. So this is the architecture of our pipeline. We deliver 3 optimized frameworks for cosmic shear, 2 times 2-point, and the full 3x2-point in both ΛCDM and wCDM with massive neutrinos. The model has around 60 parameters in total: cosmology, baryonic feedback, and intrinsic alignment for cosmic shear, galaxy bias and lens magnification for clustering, plus a full set of data calibration parameters. Critically, some of these priors are externally informed by image simulations and cross-experiments constraints, and the entire pipeline is validated while data blinded, freezing all modeling choices before ever touching the real data. So let me show you how that blinded validation works. So the central challenge of this work is the following: how do you validate a pipeline without looking at the real data? The answer is a fully blinded process. We start first by generating a synthetic noiseless signal, a mock data vector, assuming a fiducial cosmology. This is with realistic redshift distributions and analytical covariance metrics. We then deliberately contaminate this mock signal with the theoretical systematic we are most worried about. This could be baryonic feedback, galaxy bias modeling, and intrinsic alignments. And the question we ask is, if our model is wrong at small scales, how badly does it bias away cosmology? This is where the scale cats come in. We iteratively remove small-scale data points until the bias in the recovered cosmology drops below our threshold. Only then, when do freeze the pipeline and declare it validated. The real data is never touched until all of this is frozen and done. So we remove small-scale modeling uncertainty separately for each probe. For cosmic shear, we address baryonic feedback and nonlinearities of the matte-power spectrum together, while for the 2 times 2-point and 3x2-point, we additionally account for potential mismodeling of the galaxy bias. So the flowchart shows the full-scale CAD design. It's a nested process where the validated cosmic shear and 2 times 2-point serve as the starting point for the 3x2-point validation. So let me focus first on the cosmic shear case to make the logic concrete. We produce contaminated data vectors that bracket our uncertainty, a high feedback scenario, and a gravity-only scenario. We then run an MCMC with our baseline model, progressively tightening the scale cats by removing data points with an increased delta chi-square. Our validation criteria is simple. The shift in the recovered set must stay below the 0.5 sigma level. If it does, okay, the cats are validated. If not, we cut more scales and repeat. So here's a concrete example of the scale cats in action for the cosmic shear. Baryonic feedback, which is driven by active galactic nuclei outflows, redistributes matter and suppresses the power spectrum at small scales, as you can see in the green curve for the Bahamas high feedback scenario. Our baseline model, which assumes HM code 2020 with a fixed amount of baryonic feedback given by log TAGN of 7.7, is shown in purple. We validate our scale cats against two extreme bracketing scenarios: a gravity-only universe in which there is no baryonic effects, and the strong feedback scenario described by Bahamas 8.0 model. The vertical line shows progressively stricter cuts. Moving right means cutting more data points. And our criterion is that the shift in recovered SA stays below the 0.5 sigma for both scenarios. This is defining the validated delta chi-square threshold for the cosmic shear analysis. So now the key question is, how do we know our model is robust? We answer this with analysis of synthetic data sets while fully blinded. We analyze mock catalogs and noiseless theory vectors, demanding that the small-scale systematic bias cosmology less than 0.5 sigma. For the linear analysis, we go down to minimum scales of 9 megaparsecs in UFO-H for the galaxy clustering and 6 megaparsecs for galaxy-galaxy lensing. The nonlinear galaxy bias analysis, for which we use FastPT, pushes down to 4 megaparsecs for both. The figure shows the omega m S8 plane. The black contour is our baseline. The color contours are deliberate stress test with excessive feedback, no feedback, alternative galaxy bias models. All posterior means fall within the 0.5 sigma threshold. So the pipeline is validated and robust, and we can trust the cosmology that we extract from the real data. Now that we have validated the pipeline, let's ask a more ambitious question. What if we had a complete theoretical description of small-scale physics and could use every data point that we measure? So this plot shows exactly that comparison. The black contour is our fiducial nonlinear galaxy bias analysis down to 4 megaparsecs, while the pink contour uses all angular scales, marginalizing over the baryonic feedback strength. The result is a factor of 2 gain in constraining power, and notably, it also reduces the projection effect we see in the fiducial analysis. This tells us something important. Half of the cosmological information in DS-GR6 is currently inaccessible, locked behind our incomplete understanding of small-scale physics. This is the frontier for stage 4 surveys for the coming generation, and it leads directly to the lessons I want to share. The 3x2-point model requires a high-dimensional parameter space, accounting for cosmology, astrophysical systematics, and data calibration, adding up to around 60 sample parameters. This high dimensionality creates a counterintuitive situation. So adding a more complex parameterization does not always help. For example, switching from linear to nonlinear galaxy bias adds 6 extra parameters per redshift. Yet the gain in constraining power in ΛCDM is only 4%, as you can see in the nearly identical contours here. In wCDM, the nonlinear case is actually worse, as the extra parameters dilute the constraint on W. So the lesson is clear: complexity without external information is not for free. For stage 4 surveys, we will need external informed priors on higher order bias coefficients, baryonic feedback, and intrinsic alignment that might come from dedicated simulations and cross-experiment constraints. Otherwise, we risk paying a high parameter space cost for minimal cosmology return. Second lesson concerns projection effects. When you have mildly constrained parameters in a high-dimensional space, the act of marginalizing down to 1D or 2D posteriors can shift the recovered values away from the truth, even when your model is perfect. This is not a bias, it's a geometric artifact of the prior volume. And this becomes a serious problem in scale cat validation, as we see in the figure. The x-axis uh, shows progressively stricter cosmic shear cuts moving to the left. And one might expect that cutting more scales, this is removing more contamination, should bring the recovered essay closer to the input value. But in the cases highlighted here, this is the opposite. Stricter cuts reduce constraining power, amplifying projection effects, which increases the apparent shift. You cannot tell whether you are seeing a mitigated contamination or projection artifacts. Our solution was twofold. Use the 2D posterior plane as the validation metric rather than the 1D essay shift, and report both the posterior mean and the maximum a posteriori value in the real data results. This distinction will become increasingly important for a stage 4 surveys with even larger parameter space. And the third lesson is on the computational front. The scale cut validation process requires running hundreds of MCMC chains across all probe combinations in ΛCDM and wCDM and require 1.75 million CPU hours. That's just for validation, not the actual data analysis. So the breakdown is telling Cosmic Shear took only 33 runs at 3 hours each. This is fast, but the linear and nonlinear galaxy bias validation require around 90 runs at 36 hours each. This is where the cost explodes. So for stage 4 surveys, LSST, Euclid, Roman, with larger data sets, more tomographic beings, and more complex systematic, this approach is, as it is right now, is not sustainable. The path forward requires PK emulators, machine learning accelerated likelihoods, more efficient sampling algorithms. And these are not nice to haves for next generation 3 cross 2 point analysis. This will make the difference between feasible and successful analysis. Finally, I will just close with the key takeaways. We have delivered validated per probe optimized analysis pipelines for the DS-GR6 3 cross 2 point in ΛCDM and wCDM, controlling small scale systematics to below 0.5 sigma, down to 6 megaparsecs for the linear galaxy bias analysis, and down to 4 megaparsecs when we include the nonlinear description. There is a factor of 2 gain in constraining power waiting for us at small scales, and unlocking this information is one of the central challenges for the next generation of surveys. The methodology presented here and the lessons that we have learned provide a direct foundation for Euclid, Roman, and LSST. And all DS Y6 papers are available at the link available right here. And thank you for listening. I'm looking forward to the discussion.